Welcome back, guys. Today we're going to be starting motion in 2 or 3 dimensions. So really it's just going to take the ideas from kinematics that you previously learned about velocity and acceleration and such, and it's going to apply them to multiple dimensions using the vector methods that we learned last class. So it's just going to be taking those ideas that you should already know and combining them a little bit mathematically. So buckle in. This is going to be starting in chapter 3 of our textbook. We're going to be in section 3.1 first. That is position and velocity vectors. So we're just going to take those that we done in 1 dimensions and expand them out to 2 or 3 dimensions. And the way we're going to do that is with our notation from last class or last lecture, whatever you want to call it. Our position vector is still going to be r. And now it's going to be notated as however far in the x direction you are with the I hat for the unit vector, that's the x direction, plus the y component in the y direction, which is the j hat, plus the z component in the z direction, which is the k hat. So that is your generalized position vector. You could notate any position in space using that vector with an x, y, and z coordinate. So we can redefine a few things now that we have that as our generalized position vector. One of those is the delta operator. Okay, so the delta operator, and we'll say the delta operator with our position function, that's displacement. Change in position is displacement. That is still going to be final minus initial. So you could say you have a final minus initial position. And we're going to see what that looks like mathematically with our vector notation. So our final for the position would look something like this. Your x coordinate final in the I direction plus your y coordinate final in the j direction plus your z coordinate final in the k direction. And then our initial looks the exact same, except all these are for initials rather than for final. So you end up with these 2 vectors, and then you have to subtract them to get your delta r. So if you subtract those 2, you're just doing this times -1 and adding them together, you get xf I hat minus xi I hat plus yf j hat minus yi j hat plus zf k hat minus zi k hat. And you can make this look a lot better if you just factor out your unit vectors. So you can factor from this first term, or these first 2 terms, the I hat out. So you could say that's xf minus xi in the I direction or the x direction. And you can factor out similarly the j hat and the k hat. So you simply get final minus initial for each individual component in each direction. So your delta r would equal this big guy. And that makes sense. You're just subtracting each coordinate, the final minus the initial, and then putting it in its direction. So if we took that and wanted to do something like average velocity, we would say that change in position divided by change in time equals your velocity on average. So your velocity vector would then be like your displacement vector divided by delta t. So our displacement vector that we just wrote was xf minus xi times I hat plus yf minus yi, sorry, that was a bad I, j hat plus zf minus zi k hat. And to make that velocity, or average velocity, you divide all of these by delta t. And that ends up being your average velocity formula right there in terms of multi-dimensions. But the reason we're all here is not for average velocity, it's for that fun instantaneous velocity that you have to use with calculus. I can't spell instantaneous while talking. Instantaneous velocity. So the formula for that one was that velocity equals the derivative with respect to time of your position function. Now you can take functions and have them as components of vectors, and that sounds really weird, but you could also write your r position as a function, which we've seen before. During our first lesson we took the position function and did the derivative and got the velocity. You can have functions as your components for things, okay? So for example, you could write a generalized r vector in terms of functions. So this could be the x function as function of time in the I direction, plus a y function in the j direction, plus a z function in the k direction. So you can have functions for each of those different components, the x, the y, and the z. And then in order to take the derivatives, or to find the velocity, you just take the derivative of each function with respect to time. So this would be dx of t dt in the I direction, plus dy of t dt in the j direction, plus dz of t dt in the k direction. So let's go ahead and go do an example that covers that. This is example 3.1 from the book. My Wi-Fi out here is sucking, so I'm just going to write the problem down for you. So the question says, a robotic vehicle is exploring the surface of Mars. The stationary lander is the origin and the surface is the xy plane. The rover has coordinates x equals 2 minus 0.25 t squared and y equals t plus 0.025 t to the third. Question A is find coordinates and distance at t equals 2. Part B we're skipping because it's going to be long and tedious and not helpful. Part C says find the expression for instantaneous velocity and find the velocity at time equals 2. So I'm going to make this a little bit smaller real quickly. There it goes. And we're going to do part A. Part A says find coordinates and distance at time equals 2. This isn't too bad. You just got to plug 2 in to each of those functions. X equals 2 minus 0.25 t squared equals 2 minus 0.25 times 2 squared, which is 4, so that ends up being 2 minus 1. Your x is 1 meter. And then for y, you've got y equals time plus 0.025 t cubed. So that's 2 for time plus 0.025 times 2 cubed, which is 8. And if you do that, you get 2.2 in meters. So your xy coordinate is 1 and 2.2. Now in order to get the actual distance, not just the coordinates, you got to do the magnitude of that vector or of that coordinate. So it'd be Pythagorean theorem, square root of 1 squared plus 2.2 squared, whatever that is. I'm not going to pull out a calculator and figure it out. So that's part A. Can't make that any smaller. Okay, now we move on to part C. I'll do it over here on the side. Part C says find an expression for instantaneous velocity. So let's write this in terms of our vectors. Our r vector is equal to the x component, which is 2 minus 0.25 t squared in the x direction, which is I, plus t plus 0.025 t cubed in the j direction. I'm struggling to have enough space there. Moved it over. And that's in the j direction. So that is our generic vector applied to this situation. We've just got the function for x in the place of x, the function for y in the place of y. Now to find velocity, we just got to take the derivative of those with respect to time. The derivative of 2 minus 0.25 t squared is negative 0.5 t in the I direction, plus derivative of t is 1, plus 0.025 times 3 is 0.075 t squared in the j direction. So that's your velocity vector at any point in time. Now let's do time equals 2, because that's what our question wanted. At time equals 2, velocity just has 2 plugged in for time in all the places. Negative 0.5 times 2 is negative 1. And that's in the I direction. And then we've got 1 plus 0.075 t squared, so that's 0.075 times 4, which is equal to 0.3. So we get 1.3 is our j velocity, or our velocity in the y direction. And that's the whole thing. Your velocity is going down, or not down, sorry, to the left and up, with negative 1 for the x and 1.3 for the y. So what that did was it saved us from dealing with a Vx and a Vy separately and having to calculate a bunch of different things. We were just able to calculate it all there within one equation. Now if you wanted to find the actual magnitude of that, since these are just the x and y components, you could do Pythagorean theorem again. So that would be negative 1 squared plus 1.3 squared. Take the square root of, you'll get whatever the velocity is. And if you wanted to find the angle, you could also set that up as a triangle. Say, oh, that's a bad triangle. Let me do that again. You could set this up as a triangle. Goes negative 1 in the x direction, 1.3 in the y direction. So that would be a 1. That's a 1.3. And you can find this angle using inverse tangent of opposite over adjacent. So 1.3 divided by 1. And if you're in degrees, that'll tell you that angle in degrees. So you can get the magnitude and direction using Pythagorean theorem and inverse tangent. Now the same thing is going to happen with acceleration. We're just going to take our old definition of acceleration and apply it to what we already have. So our new definition of acceleration is that it is equal to the time derivative of the velocity function, or the second time derivative of the position function. So you could just apply that to our vectors like we already have. R was a function of, or x is a function of t in the I direction, plus y is a function of t in the y direction or j direction, plus z is a function of t in the z direction or k direction. And then we took the derivative of that to get velocity. So we had that's equal to d dt of x of t I plus d dt y of t j plus z, not z, plus d dt of z of t k. And then to get, sorry, this looks like an R. That's supposed to be a v for velocity. And then to get your acceleration vector, all you got to do is take the derivative again. So you're doing d squared dt squared x of t, y direction, second derivative d squared dt squared of y, j, plus d squared dt squared of z of t, k. So you're just taking another derivative to get some acceleration. So if we were going to take this and apply it to the previous problem we did, I'm going to make this smaller. Can't really scoot it down. And we said our x was 2 minus 0.25 t squared, and our y was t minus 0.075 t cubed. To get acceleration, you just have to take the second derivative of both of those. So your acceleration in the x direction is second derivative. So that's 2 minus 0.25 t squared. To get the first derivative, you get negative 0.5 t. So you get negative 0.5 in the x direction. And then you have to do the same thing for the y. Take the second derivative. First derivative is going to be, I'll write it down first, 0.075 t. First derivative, the t turns to 1 minus 0.075 times 3 is 0.225. And then that's going to be t squared. Then we got to take the derivative again. We get negative 0.45 t in the y direction. So it's minus 0.45 t for the j direction. And there was no given z, so we just leave it out. And that is your acceleration at any point in time for that scenario. So the beauty of this is that you can now work entirely within one equation using only derivatives and the vector notation, and it's going to pop out all sorts of kinematic goodness. And we're going to apply that tomorrow or next class or next video, whatever, to projectiles and relative velocity. But for today, bask in the glory of just the two-dimensional, three-dimensional motion and do the problems that are assigned in Google Classroom. And like with any other YouTuber, feel free to like and subscribe. If you want to get more videos, you can click the bell for notifications. Leave your thoughts in the comments below. Love to see you there.